All right, let's get into it. Today, we're basically chemical detectives. We're going to crack a case where a tiny change to a molecule completely transforms it. And together, we're going to solve the mystery of why that happens. So, you ready? Let's dive in.
So, our whole mystery starts with what looks like a magic trick. You can start with one compound, and just by swapping out one little piece, boom, you get a totally different one. It seems so simple, right? But that one tiny change alters its entire identity. And the biggest clue we have? The color. So what on earth is the secret?
Now, the subjects of our investigation, our two main suspects, if you will, are these complex ions. They look a little different, sure, but they're both built around the exact same metal atom in the center, manganese. The only thing that's different is what's attached to it. And yet, that one little difference changes absolutely everything.
And that brings us to the biggest question of our whole investigation. Why? Why are these two compounds, with the same manganese heart, so wildly different? How can just swapping out some chloride for cyanide have such a huge effect, especially on something as obvious as their color?
You know, every good investigation starts by identifying the main player. And our first clue lies right there, with that manganese ion sitting in the middle of it all. To really get what's going on, we first have to figure out its electric charge, what chemists call its oxidation state.
Let's do a little detective work together. In both of these molecules, the total charge is -4. Okay? We also know that each little piece attached, the chloride or the cyanide, has a charge of -1. And since there are 6 of them, that's a total charge of -6 from those guys. So what does the manganese's charge have to be for the whole thing to add up to -4?
You got it, it's +2. So in both compounds, we're dealing with the exact same manganese ion. And honestly, that just makes the mystery even deeper. If the core is identical, then the huge difference between them has to come from the only thing that's different, those molecules surrounding it.
Okay, so this brings us right to the heart of it all, the secret of color itself. It turns out the color we see isn't really about the atoms themselves. No, it's all about how their electrons dance with light. This is our big aha moment. So here's the bottom line. Color is all about energy. More specifically, the energy levels of electrons. See, when a compound absorbs light, an electron gets all excited and it literally jumps from a low energy level to a higher one. And the color of light it needs to absorb depends entirely on the size of that jump.
The scientific tool that lets us crack this case is called crystal field theory. Now, it sounds super complicated, but the main idea is actually pretty simple. It just describes how those surrounding molecules, we call them ligands, mess with the electrons of our central manganese ion and change their energy levels. Think of it like this in 4 steps. First, the ligands close in on the metal. Second, their negative charge pushes away the metal's own electrons. Third, this push isn't even, so it splits the electron orbitals into 2 different energy levels, a low one and a high one. And fourth, an electron can then absorb just the right color of light to make the leap across that energy gap. We call that gap delta O.
And this, right here, is the key to our whole mystery. Not all ligands are the same. Some, like our chloride, are weak field ligands. They don't push on the electrons very hard, so they create a small energy gap. But others, like cyanide, are strong field ligands. They push way harder, creating a much larger energy gap. And that difference, well, that difference is everything.
So now that we have the theory down, we can finally look at the hard evidence. We're going to check out the light absorption graphs for our two compounds and connect all the dots to solve this thing once and for all.
All right, here's our evidence. Over on the left, we've got the lab results, the absorption spectra for our 2 mystery compounds, A and B. The peak of each curve tells us exactly which wavelength of light each compound loves to soak up. And on the right, well, that's our secret decoder ring, the color wheel. We're going to use it to translate the color that's absorbed into the color we actually see.
And here is the simple rule that cracks the code. The color we end up seeing is not the color the compound absorbs. Nope, it's the complementary color, the one directly across from it on the color wheel. So if a compound absorbs green light, it's going to look red to our eyes.
Let's put all the pieces together. The cyanide complex has those strong field ligands, right? So it creates a large energy gap. That means it needs higher energy light, like blue light, around 470 nanometers to make that electron jump. That lines up perfectly with curve A. And since it absorbs blue, what do we see? Its complement, orange. Now for the chloride complex. It has weak field ligands, creating a smaller gap. It only needs lower energy light, like green light, around 530 nanometers,
which perfectly matches curve B. And because it absorbs green, we see its opposite, red. And just like that, there it is. By putting all our clues together, we've totally solved the mystery. We know which compound is which, but even more importantly, we know why they have the colors they do. Case closed.
But hang on, let's look at one last cool piece of this puzzle. For that chloride complex, the energy gap is super small. This means it's actually easier for the electrons to just jump up into the higher orbitals than it is for them to squeeze together and pair up in the lower ones. We call this a high-spin state, and it's a direct result of having that weak field ligand. The cyanide complex, on the other hand, would be low spin because that big energy gap forces the electrons to pair up down below.
So, if you only remember one thing from all of this, let it be this simple chain of events. It all starts with the ligand. The type of ligand determines the size of the energy gap. That gap determines which color of light gets absorbed, and the absorbed light defines the beautiful, vibrant color that we actually get to see with our own eyes.
Now, the same exact principles we just uncovered are what give a ruby its deep red color and a sapphire its brilliant blue. It's this exact chemistry that paints our world. What we looked at today was just one case file, but this science is hiding in plain sight, absolutely everywhere. The only question is, where are you going to see it next?